Okay, so for this problem, similar to the last one we did without friction in terms of the configuration, we have a 2 kilogram mass on a surface. String connects the 2 kilogram mass to a hanging mass of unknown mass little m. And the situation now is we have static friction, which is 0.5, and what we'd like to do is we'd like to conceptually determine how much mass to add to this to just begin to move big M. And so if we didn't put anything here, big M wouldn't move. If we put just a tiny little weight like a tenth of a gram or something here, it still wouldn't move. So we're going to have to increase this until we get enough weight to overcome the static friction, but just to have everything be in equilibrium. So essentially then that means that the acceleration A for big M is 0 and the acceleration A for little m is 0. The direction 0 is indicated here in the drawing. So here now is a free body diagram for big M, and there are two vertical forces. And in typical fashion, these two cancel each other, and in this case, t and f sub f also cancel each other since the horizontal acceleration is 0. So I can conclude from the horizontal forces t minus f sub f, this is the frictional force, is equal to 0. So t is then, the tension is then equal to the frictional force, but frictional force, static frictional force is equal to mu sub s times n. But since we know that n is equal to mg, that's a Newton number 3 conclusion from a sub y, which is 0. We can replace mu sub s times n with mu sub s times mg, because n and mg are the same. Now I go over and I do a free body diagram for the hanging mass little m. And there are two vertical forces that act on it. The same horizontal tension that acts to the right on big M acts upwards on little m. And then there is, of course, a downward non-contact force, little m times g, its weight. But that's also 0 if you're just on the cusp of moving, which is the assumption in the problem here. So that means that the tension is equal to the weight of little m. So now I can take the expression for t and plug that into here, which allows me to conclude that mg is equal to mu sub s times big mg. The g's on both sides of the equation cancel, and I conclude that the required little m to just get this moving is mu sub s times big M. Mu sub s is 0.5 for this problem. And remember, this is characteristic of these two surfaces, the surface of the table and the bottom surface of this big M mass. 0.5 times the big mass, big M, is 1 kilogram. And so 1 kilogram, the system will just barely be in equilibrium, and if I increase this 1 kilogram at all, it will now transition to kinetic friction and to some acceleration.